Thank you, Marit. So let's get started. And today's content on my presentation, and the content is visible here. So basically, I'm discussing about the distance protection in general and also the functionality of our relay. And then I'm going to summarize the whole package. And after that, Emil will do the distance relay Omicron-based testing. And overall, our AQ250 line, we got the feeder relay F255, and if we add a letter to the end, for example F255A, we get a regular feeder protection relay. But if we alter the last character, for example B or C, we got line differential relays. And the C model comes with a backup feeder protection as well. And the model D stands for distance protection plus feeder protection as a backup. And E is the most the largest or comprehensive model. We got line differential relay as a line differential relay as a prime protection, and then as a backup we got distance protection and also feeder protection. And today we are going to discuss about the distance protection primarily. And what is the segmented distance protection about? What's the idea? What we are going to bring on the table? And first of all, let's have a look of a quick video. It also includes some sounds, so if you probably already got them sounds on, so please enjoy. Let's get started with the distance protection, the models D and E. And first, I'd like to discuss briefly about the challenges when it comes to distance protection. So basically, what we bring to the table and what we try to cover better than before is that, for example, if you got improper resistive reach configured in the relay, or the system conditions they can lead to several issues. And now I'm pointing especially two separate issues, and one is the underreaching for high resistance faults. If the resistive reach is too small, or it's set too small in the relay may fail to detect the faults with significant resistance. Such faults are high impedance ground faults, arching faults, or tower footing resistance. And on the other hand, if the setting is overreaching on external faults, so if the resistive reach is set too large, it can cause the relay to overreach, detecting and tripping for faults outside its intended protection zone. And such tripping can come from adjacent lines or basically during double earth fault. So now representing our solution for this. So basically this is a little bit color coded. So on the right hand side we can see the picture. We got a protected line and we got three stations A, B and C. So the setting line segment can be individually set. So we got 3 lines, 2 lines between stations A and B, and then we got 1 line between stations B and C. And then on this picture, we can see that we got 2 distance protection zones, zone 1 and zone 2. And the blue, we got both colors, green and blue, and the blue stands for the resistive ridge. And now what is special in our relay is that the resistive ridge, it follows the set line throughout all used zones. And in our relay, you can have up to 10 zones. Then each face-to-face zones and face-to-ground zones. And so basically we can follow with all those zones, we can follow, or the resistive ridge can follow the protected line that we are separately setting here. And this also, through this, we also get improved, more precise fault locator due to the new line modeling. And we are also going to check and test this later today. And one benefit is also that we get more efficient control over the outer reclosing functionality through different zones. For example, in case here we have 2 protected zones, but we can also add extra zones where we do the auto reclosing only, for example, when the overhead line, when the fault happens on the overhead line. But if the fault happens on the cable, on the underground duct cable, then we can block the auto reclosing and it will never happen. So there are these types of benefits here. And also about them, the distance zones themselves, like mentioned on previous slide, we got 10 zones, and all zones are freely configurable. They can be unidirectional, forward-looking, or reverse-looking characteristics. And we don't have the MHO characteristic, but we have the quadrilateral characteristics available. And of course, there is, as seen on these pictures, we got zone-specific load encroachment area. And we can also enable separately power swing blocking and pole slip or out-of-step tripping in our relays. And of course, we are going to have a look how to do easy-to-use transfer trip as a default in all line protection relays. We do the transfer trip to receive faster operating times in our zone 2 trippings. And let's get started. So this slide here and these pictures here, they are related to the very first slide we saw a few pages ago. So that orange line is now here. So the orange protected line, which consists of 3 segments, is now here. So we got 2 lines between stations A and B, and we got 1 line between stations B and C. And on the right-hand side down there, we can see the line segment 1, 2, and 3. So the line segment 1 is a 45 kilometer long overhead line, and there are resistive reactive values there available with these lines. Resistive values are 0.267 ohms per kilometers, and the reactive values are 0.33 ohms per kilometers. And normally you get these values from the cable manufacturer. They are normally primary values, and you get them from the brochures, and they are ohmic values as per kilometers. So a second line, we can say it's also 45 kilometers with its own resistive reactive values, and the line 3 is basically underground cable, and the length is 75 kilometers. And up there, I'll just hold this. Yes, up here we got zone 1 and zone 2 settings. So zone 1 is underreaching between stations A and B by 20%, so the total reach is 80%, and zone 2 is overreaching the station B by 20%, so the zone 2 reach is in total 120%. And as we can see, with these ohmic values as per kilometer and 45 kilometers of this segment 1 line, we get the reactive reach of roughly 15 ohms and the resistive reach 12 ohms with the line 1. This is where the line 1 ends. And if from here we continue with another line, and it ends at the station B, where we got ohmic values of reactive 36 ohms and resistive 16 ohms. Then the underground cable between station B and C, and here are our ohmic values at the end of line 3. And as per these values, this 80% of zone 1 reactive reach corresponds to roughly 29 ohms, and this zone 2 120% reach corresponds roughly to 40 ohms. And now when proceeding to next slide, this graph here on the right hand side is basically screen capture taken from our relay. So this is how we start by setting the orange line that we are actually protecting here. So we know that it now consists of 3 separate lines, 2 overhead lines and 1 underground cable. So firstly we start by selecting just 3 segments, because we are protecting 3 lines, we choose 3 segments. And then the second setting, you have this setting with each protected 3 lines, how we want to set our ohmic values. So we can give the right direct endpoint of the line by putting R and X values directly, or we can set the protected line impedance values as per Z and its angle. And of course, we can also use ohmic values as per kilometers, and this is what we are using in this example. And this is also my favorite way to set the relay, because we normally get these parameters from the cable manufacturer directly. And these we do ohmic values as per kilometer. So basically, the values we saw on the slide, we put them here. 0.26 is the resistive reach in line 1, 0.33 resistive reach of a reactive reach of line 1, and the length of the first overhead line is 45 kilometers. Second line is here, it's also 45 kilometers for a little bit different parameters. And then we got the third line, which is underground cable, and it's 75 kilometers of length, and the resistive reach is way higher because of the cable characteristics. And then we also have the reactive reach here. So this is how we set those 3 protected lines. And once we move forward, then we need to also, on top of setting those 3 protected lines, we also need to set the compensation factor for those lines. And in our relays, even though we got now 3 protected segments, we only set 1 compensator factor for all those 3 segments. And that line compensation factor can be also set in 3 ways. It can be the total R per X value between stations A and C, or it can be the R and X as per ohms. But in this example, to create some variety, we are using the Z, the impedance value and its angle. But since we don't have any real network behind us, so we don't have any real values to set here. Therefore, I'm just putting the impedance value as per 1 ohm, and the angle is 0 degrees. But this, if you have you have a system and your grounding factor is measured, this is where you actually put those values. And by setting only 1 grounding compensation factor for all 3 segments, I mean that instead of doing them individually here, we only do it once from between the station A and C. We have only 1 compensating factor. And we do this to keep the setting of the relay more simple in the way of grounding factor, especially when you need to put all these settings to your test equipment, let's say Omicron or similar, or do the calculations for these. So at this point, at least, we have decided to stick with only 1 compensating factor for the whole total protected area. And so next, what we have here, this is our goal on the left-hand side. And this is the actual, based on the settings that we just set to the relay, this is a copy copied print screen from our relay. So basically the characteristic and ohmic values are identical in this already at this point. And now when moving forward, as I mentioned earlier, we are setting all those ohmic values as per primary values. But when it comes to relay scaling, how we scale those values, if you want to, for example, do the commissioning, or you, for some reason, you want to have secondary ohmic values, it is also possible. You can scale these measurements and settings. You can scale them instead of doing primary. You can also change them into secondary values if you want. And the zones are now enabled here. We have enabled 2 zones like it was meant to be, and both zones are only protecting to forward direction. So both line to line and line to ground zones, we choose separately that the direction of protection is only forward in this example. But if you need to go reverse or unidirectional, you just do it here. But in our example, we do only protection to forward direction. And there is a separate primary or main setting for the following that I'm going to show you here. So we got load encroachment area, we got power swing blocking, and then we got out of step or pole slipping functionality. So basically all these 3 has to be manually enabled in our relay. This is the general manual enabling, but when we go into zone specific settings, we also need to activate all these separately in under each zone. So this is the general activation of load encroachment, power swing, and out step. But we're gonna have a later look how to do them, how to activate them under each zone separately. And basically here it already is. So firstly, we got 3 protected line that we already have set. So the zone 1, how many of those line segments we want to follow? If we want to follow with the resistive reach with all those lines, we choose all those 3 segments here. And this is what I recommend to do. If you just put 1 here instead of following all those 3, you would follow the resistive reach of zone, I mean protected line 1, but once that line 1 ends and you proceed to the next line, the resistive reach would not follow the line 2, but it would stick with the same angle where it ends with the line 1. So if you want to follow or use the resistive reach through the whole protected area, you choose the same 3 segments here that you are actually protecting. And of course, you are setting here the resistive and reactive reaches of them zones. And this is also where you enable the load encroachment area under this specific zone, and where you also enabled power swing blocking under the specific zones. So load encroachment and zone power swing are now is used under this zone. So you need to do this separately under both zones 1 and 2 if you want to use the power swing blocking and the load encroachment as well. So now after simply just enabling those 2 zones and setting the resistive and reactive reach there, and also enabling the load encroachment area. So now we can say that on top of this protected red line here, we also have zone 1, which is yellow, and zone 2, which is basically blue. And since we choose that this is our protected line here, and since we choose that both zones are actually following all line segments, so we can say that when the line segment 1 ends, the resistive reach angle also changes, and the resistive reach angle also changes here again. So now we are following the resistive reach all 3 protected lines. And if we would put only that we follow only the resistive reach of line 1, this angle here would not change, but it would proceed like this. So this is where we actually need to put the setting value 3, like we are also doing with the line protection. And as we are moving forward, there are also some extra parameters in our relay. For example, if for some certain reason, for example, measurement accuracies or similar, you want to restrict your resistive reach of at certain point. So as a default, the resistive reach restrictions are off. The value is 0, which means it's off. But if you put, let's say, 40 ohms there under the zone settings, that would cut or restrict the resistive reach to maximum 40 ohms. Once you get to that 40 ohms, it would stop there and just slide with that 40 ohm all the way to the next. If we add another zone, third zone, fourth zone, so on, the resistive reach wouldn't grow. So this is one special setting that we got under the relay, but in our example now we are not using this resistive reach. And also the load encroachment can be set checking the forward direction, reverse, or unidirectional. So basically, in our example, the load encroachment is only pointing to forward direction, or we have one load encroachment settings here. But if you choose unidirectional, you would get another pair of settings here under the load encroachment. So basically, you would need to have separate settings for load encroachment to forward direction and also another set of settings to reverse direction. But since we are only having 2 zones forward direction, we only need to have one load encroachment, which is also forward direction. And briefly about the power swing blocking or out of step tripping. We have done lots of testing with power swing and out of step functionality. And even now that the release is still not fully there, but it has evolved a lot of testing. So what we have achieved by doing a lot of testing, we have achieved that first of all, this is not impedance related power swing blocking. We don't need we don't need to set any blinders on outside the protected zones. This power swing blocking is based on change of phase current, so it's a delta I. This is how we detect the power swing. So basically, how do we enable it? We only choose enable power swing, and then we activate it under individual zones. You don't need to do any other settings with the power swing. So basically, this is just enable it, and everything else is already taken care of. And what comes to the out of step tripping or pole slipping, there is one setting under that. So basically, the default setting, how many slips in the power generation you need to have to actually trip for the from the out of step. So as a default, this setting is 2. So basically, the power generation needs to slip 2 times before we activate the tripping output. And this tripping output as a default is not directly connected to anywhere, but you need to actually choose how you want to use this auto step tripping. If you want to connect it into an actual output of LED or send it to SCADA, you need to do it manually. And you can also choose to alter the number of necessary actual pole slips to actually have the trip. For example, you can change it between 1 and 10, or I don't even remember, but I think it's relatively the highest setting is too large anyway, nonetheless. But as a default, it's 2. And then about the transfer tripping. So in our case, when I say transfer trip, I mean permissive overreach transfer trip. And what it means that if we have a fault here in the beginning of close to the station A, the station A distance relay would say this close fault and the zone 1 would trip immediately. But what happens with the opposite station B relay. The station B relay sees that fault on zone 2. And there's probably some time delay when we are discussing about zone 2. So the other end would trip this fault away probably, let's say, in 300 milliseconds or similar. And at this point, what we want to activate this transfer tripping functionality to receive this permissive overreach transfer trip. So what we do, whenever, let's talk about relay at the station A. Whenever the zone 2 notices a fault, we use our integrated transfer tripping functionality where we can send data to the other end of the relay. We use this inbuilt process bus for this. So we choose zone 2 starting, let's say zone 2 face-to-face starting, and zone 2 face-to-earth starting. Whenever this happens, we send a signal to the opposite side relay. And once the opposite side relay receives this signal, it is connected in the programmable logic in parallel with its own zone 2 starting. So whenever the zone 2 at the station B is starting and it receives this close fault signal from the station A, we can perform this transfer trip in a few milliseconds later after the station 1 zone 1 trips. So basically, we don't need to wait for additional 300 milliseconds with the zone 2, and we can trip right away. And basically, the operating time of our transfer trip, which has been built inside our separate bus, basically, the operating time is roughly 1 to 2 milliseconds. But we can also have a look later today because Emil is going to show you in real life demonstration with a real life demonstration how fast it is. So we're gonna have another glimpse of that later today. And the very final setting that we have related to the distance functionality is the voltage transformer supervision. And this is not the regular VT supervision, but it's the independent. It's separately built for distance protection. So it's integrated under the distance protection. It's the fast VT supervision. And how you enable it, you don't need to basically, as a default, it's already there. And all the wiring is done or integrated inside the relay. So basically all the blocking happens automatically. You don't need to activate any blocking or similar. You just enable this fast VT supervision with 3-phase. There are 2 modes. You can use the 3-phase mode. Whenever you notice any type of fault, you block all 3 phases. Or then there's another mode which is phase individual. So basically, if you notice a phase to ground fault, you can only block that area. Only that area, not the rest of the network. So basically 2 modes, 3-phase and 1-phase. And then about the commissioning once again. So this picture is taken from the relay. Once the primary scaling to primary setting was changed to scaling to secondary. So basically the settings I set there as a primary, but I then altered the setting to secondary. So we can now see the characteristic in secondary mode. If this helps you with the commissioning, you're welcome to do it. And now we can see instead of having like 40 or 30 ohms, we got hundreds of ohms here. And if this helps you with the commissioning, you can do it. And at the end, if we compare, our original goal is there on the left-hand side, our protected zone, our protected line between 2 stations, and then our 2 zones. And this is a screen capture taken from our relay. We got exactly with same ohmic primary values. We got the protected line and these 2 zones, zone 1 and zone 2. And even though I think our distance relay release is about to happen at the end of this month, end of March. But We have done a lot of testing, and we also have some pilot projects ongoing. We have our distance protection already in transmission distribution networks in Europe and Central Asia. And we also have delivered to a power plant project in Central Asia. And there are also numerous projects, those are currently underway, not finished, but underway in Europe and Asia as well. So even though this is not fully released, but we have been doing a lot of testing, a lot of projects already. So we are in a quite good hands at this point. And once the release is out there, we can start distributing. And a few words as a summary about the benefits. So basically, once again, we got line-specific configuration between stations. And the resistive reach can follow all the set protected distance zones, all the way from zone 1 to zone 10. We got improved, more accurate fault location calculation due to the new segmented line model in our relay. And also Emil is going to show the accuracy for you later today. And we got due to these zones, we got more efficient control of auto reclosing with zone specific settings. So we can do, or we don't need to do auto reclosing with overhead lines or underground cables. And also here on the right side, we can see that this is the traditional way how to set a quadrilateral distance protection, this red line here. And here we got the resistive reach. And this is the new segmented way how to set it, where we have 3 separate lines, and our resistive reach follows it all the way. So basically, if we have a fault here, which is out of the zone, we can say that the traditional distance protection would overreach and it would trip at this point. But the segmented one, it says that the fault is outside and we don't need to trip here. The problem is probably on the adjacent line, or there's a double layer fault or something, which is not our concern at this point. So here are the benefits. But of course, without distance protection, you can go with the traditional way as well. If you want to have only one protected zone, or let's say one protected line here, like we have always done the quadrilateral characteristic, we can also do it with one line, and we in the traditional sense as well. But at this point, I already thank you, and now Emil will proceed from here. He will show you how he has prepared some tests, and we can see actually some preparation, how we have set the relays, and some test results as well. So Emil, please.
Okay, so hello from my side as well. So I will show you this quick test with the Omicron. So in this test setup here, we have a Omicron and 2 relays, relay A and B. And with the Omicron, we are testing the relay A distance function. So we are injecting the voltages and currents to the relay A, and we are then monitoring the relay A distance tripping output, as well as the power swing blocking activation and out of step tripping output. And we have connected the process bus between the 2 relays, so we can send the zone 2 start to the relay B and see the transfer tripping function in use. And we can also monitor the relay B receiving the zone 2 start signal from relay A. So that is it about the test setup. So here in the line protection module, I have configured this relay in test to be the master node, and the receiving end is the sub node. So With this process bus between the two relays, we are sending from this relay the zone 2 start signals for both line to earth and line to line loops. So these are sent here. And then we check the protected line. So this is as in Jani's presentation. So we have 3 segments here, and each segment is given in R and X per kilometer values. So these are done here, and then we have the zero sequence line settings. So these are just the K0 factor magnitude and its angle. And then we move to the distance function. So we have the 2 zones activated, and these are set in primary impedances, and right now they are scaled to secondary zones. And the resulting characteristics are shown here. So these are similar to the values that were shown in the Jani's presentation. So here in zone 1, in the settings, we have configured the load encroachment in use and power swing blocking in use as well. And for this zone 1, the operating time delay is set to 0. And for zone 2, the operating time delay is set to 300 milliseconds. And the load encroachment settings are displayed in here, and these are also given in primary ohms. And they are set in here. And lastly, we are moving to the power swing blocking and out of step tripping. So here the power swing blocking is just activated, and this out of step slips to trip setting is set to 2 slips. So that is all about the settings of the power swing blocking. So that is it about the activate configurations for now. So now we are moving to the Omicron part. So I have pre-configured this Omicron test object here to have these distance zones 1 and 2, as well as the load encroachment area to be a non-tripping zone. So usually the commissioning phase starts with a wiring test. So with this wiring test, we are checking that the measurements are okay both in Omicron and in relay. So we can just inject some impedance value, which is now in secondary ohms. And we can compare this value here to what's shown in the relay. So here the relay shows that the impedance marker is here in the zone 1 corner as it was shown in here. And with the Omicron, we can also change these impedances to primary ohms. So now that these values are in primary, we can move this impedance marker to this point and then start the injection and look at the relay and scale the zones to primary impedances and check here that the impedance marker is actually at the same point as it was in the Omicron as well. So that is now done, and we will move to the first actual test here. So this first test is to just check that the characteristics are set correctly. So here we have a couple of test points. So the relay should not operate when the test point is outside the zone and should operate according to the operating time delay setting when the test point is inside the characteristic. So let's start the test here. And this is the load encroachment area. So at this point, the relay should not trip, and inside this, the relay should trip. And every point was passed, so we are happy with that. Then usually this test is repeated with all the possible loops. So, but for simplicity, I'm just checking it with this phase 1 to earth loop. So the next test is the power swing blocking test. So with this test, we are making sure that the relay doesn't trip when a power swing is happening. So during a power swing, the impedances are encroaching the distance zone, and as we saw earlier, the zone 1 is instant. So when these impedances go inside this zone 1, the tripping happens instantly. So we don't want that during a power swing, and the blocking should stay on during this whole movement. So let's start the test. So from these outputs, we can see that the relay did not trip, and the power swing blocking signal stayed active during the whole duration of the swing. So that is fine. Then we move to the out-of-step tripping. So if you remember, for this out-of-step tripping, we had this setting of 2 slips. So we need to have this impedance trajectory going through quadrant 1 to quadrant 2 2 times. So this is the first slip, and this is the second slip. So the out-of-step tripping should happen around this point. So we will check this. And yes, the power swing blocking activates during these swings, and the out-of-step tripping activates after the second slip here. So that's okay. And then we move to this transfer trip. So in this transfer trip, we are making a fault at the beginning of the line, and this fault activates the zone 2 start signal in the relay A, which is then sent by the process bus to the relay B, and the relay B then receives it and activates its own output, and we are monitoring it with the Omicron. So we can then calculate the time delay between these two signals, which then gives us the time delay of the process bus. So here we can see that the time delay between the relay A starting and the relay B receiving the signal is only 2.8 milliseconds, so that is quite fast. And then next we have a close fault test. So here we are making a fault close to the beginning of the line with a high current. So in this case, we are expecting a very fast trip. We are talking about a subcycle trip, which is happening under 20 milliseconds, which is the time of one cycle. So with every repetition here, we are seeing that the relay operated very fast and all the tripping times were under the 20 millisecond mark. So we are happy with that. And then there is the last test here, which is the fault locator function. So here I have configured this line segment 1, which was here. The length of this first line segment was 45 kilometers, and I'm making a fault at the end of this line segment 1. So the distance to fault should be around that 45 kilometers. So I'll start the test here, and the relay tripped, and the tripping was in zone 1. So I will check the zone 1 statistic, and yes, the last fault location was very close to 45 kilometers, which was the configured length of the line segment 1. So that concludes the testing part of this.
All right, thank you, Jani and Emil, for the presentations. If you haven't yet seen our product configurator, please take a look at that on our website, arcteq.com. It's a very helpful tool for defining your products so that you find the right solution for your application. The configurator also allows you to configure your hardware and then instantly generates the complete order code for your configuration. After that, you can download a tailored datasheet with your specific configuration, so no other information, just exactly what you selected. And as a last step, you can send a request for a quotation directly from the configurator to us, and we can then respond to your inquiry. Also, on the website, you can find all the details of our distance protection relays. So please pay a visit there. And then as a last thing, please follow us on LinkedIn if you are not yet doing so. Thank you so much for joining with us today, and we look forward to seeing you next time too.